Hello ladies and gentlemen, this is Jeans from AGHAMALAYAN, and today we're going to talk about Archimedes Principle, which involves buoyant forces. So the variation of pressure with depth has a surprising consequence. It allows the fluid to exert buoyant forces on bodies immersed in the fluid. If this buoyant force is equal to the weight of the body floats in the liquid. This result was first discovered by Archimedes and is now called Archimedes Principle. So, in this principle, it states that a body immersed in a fluid is buoyed up by a force that is equal to the weight of the fluid displaced. So, in here, we're going to consider this equation. Net force upward is equal to weight of water displaced. Weight of water displaced. There. So the net force upward on the body is called the buoyant force, or BF. So this is called buoyant force, or the BF. And when the buoyant force on the body is equal to the weight of the body does not sink in the water but rather floats. Since the buoyant force is equal to the weight of the water displaced, a body floats when the weight of the body is equal to the weight of the fluid displaced. So we're going to solve some problems so that we can grasp the concept behind Archimedes Principle. So let's read this problem. A block of oak wood 5 centimeters high, 5 centimeters wide, and 10 centimeters long is placed into a tub of water. The density of the wood is 7.20 times 10 raised to 2 kilograms per cubic meter. And how far will the block of wood sink before it floats? So pause the video if you want to solve it. So the block of wood will float when the BF, or the buoyant force, which is the weight of the fluid displaced by the volume of the body submerged, is equal to the weight of the body. The weight of the block of wood is found from this equation. So W is equal to mass times gravity, and is equal to rho times volume times gravity. Or sometimes in your slides it will be written this way. So rho fluid times volume times gravity. Okay. The volume of the wooden block is V is equal to, so I'm going to change the color. The volume of the wooden block is equal to this formula. V equals A times H. Okay. Thus, the weight of the wooden block can be computed in the following manner. So I'm going to change the color of the ink again. There. W is equal to the density of the wood, that is 7.2 times 10 raised to 2 times 0. So we're going to convert all of the dimensions given here, the 5.00 centimeters and this one, into meters by using dimensional analysis. So when we use dimensional analysis to convert centimeters into meters, the our dimensions should be for 5 centimeters, it will be equal to 0.05 meters. Okay. The same with the length, or rather the width of the wood, and then the height of the wood, the length of the wood, which is now equal to 0.1 meters. And lastly, the acceleration due to gravity, 9.81 meters per second squared. So the buoyant force is equal to the weight of the water displaced, and for the body to float, this buoyant force must also equal to the weight of the block. So in other words, to represent this into symbols, so I'm just going to change the color to here. Our buoyant force is equal to, by the way, this is equal to 1.76 newtons. Okay, 1.76 newtons. Okay, newtons. So our buoyant force is equal to the weight of the water. Okay, this is equal also to the weight of the wood. So the weight of the water, by referring to that equation, this will be the formula to be used. Raw water times this formula, the volume will be this one, so AH times G, which is the acceleration due to gravity. Okay, thus we're going to use the equation that we've found. Okay, so that will be raw water times the area times H times G equals the weight of the wood. Now let's solve for H. So H is equal to the weight of the wood all over raw water, or the density of the water, times the area times the gravity. Now we have already solved for the weight of the wood, that is 1.76 newtons, and then the density of water is normally at 1 times 10 raised to 3 kilograms per cubic meter times 0.05. So we have already converted the values given in the problem to meters, times 0.1. So area is always equal to length times width. Notice that our length is the 10 centimeters long, that will be 0.1 meters, and the 5 centimeters wide will be our width, and converting that into meters, it will be 0.05 meters. And then of course the constant, 9.81 meters per second squared. Now computing for that, we will have a value of 0.0359 meters. And to make it look nicer, we're going to convert that into centimeters using dimension analysis, and we will have a value of 3.59 centimeters. In here, the block sinks to a depth of 3.59 centimeters. At this point, the buoyant force becomes equal to the weight of the wooden block, and the wooden block floats. So we're going to solve this next problem. So let's read. A block of iron has this dimension, so it is the same dimension that we encountered in the earlier example or the earlier problem. Then it is cut into 16 slices, each 5 centimeters by 10 centimeters by 5 over 16 centimeters. They are now welded together to form a box 20 centimeters wide by 10 centimeters long by 10 centimeters high. Will this iron body float or sink? The densities are given in the problem. So in here, the iron displaces a volume of water. And since the buoyant force is equal to the weight of the water displaced, it is possible that this configuration will float. We assume that no mass of iron is lost in cutting the blocks into the 16 slabs, and that the weight of the welding material is negligible. Thus, the weight of the box will be equal to here. So, the weight of the box is equal to rho times volume times gravity. And the density of the iron is given in the problem, so it is 7,860 kilograms per cubic meter. And the volume, we're going to convert all of that into meters, so 0.05 meters squared since it occurred twice, and then 0.1 meters times 9.81 meters per second squared, and this will be equal to 19.3 newtons. Now the weight of the box will be equal here. Okay, so let us solve for the depth that the iron box must sink in order that the buoyant force be equal to the weight of the box. Thus, the depth that the box sinks can again be found by the formula that we used earlier. So H is equal to the weight of the box, that is 90.3 newtons, all over the density of water times the area times the gravity. So it will be equal to the density of water is given here, so 1.00 times 10 raised to 3 kilograms per cubic meter, and of course the area, length times width. Our length is 10 centimeters in here, it's given here. Wait, yes, this is our length and this is our width. So our so this we go to the denominator. So our length is 0.1 meters, converting it into meters from centimeters, and then our width will be the 0.2 meters. Okay, so we assume that you already know dimensional analysis. And then of course the gravity, that is 9.81 meters per second squared. And the weight of the box is equal to 19.3 newtons. So our final answer for this problem will be 9.84 times 10 raised to negative 2 meters. And converting that into centimeters to look nice, it should be equal to 9.84 centimeters. Because the iron box is 10 centimeters high, it sinks to a depth of 9.84 centimeters, and it then floats. Okay, so in these examples that I have given you, the problems dealt with bodies submerged in water. But remember that Archimedes Principle applies to all fluids. So thank you for watching, and we're going to cover another fluid mechanics topic in our next video.